ஓகேப்பா, ஸ்டார்ட் பண்ணிக்கலாமா? 2 ஆயிடுச்சு. ஓகே. ஓகே.
Ma'am, thank you, ma'am. A very good afternoon to everyone. On behalf of Department of Chemistry, Vellalar College for Women, I am Dr. K. Vanitha Bharati. Welcome you all for this afternoon session of the International Seminar. It's my pleasure to introduce our resource person, Dr. B. Collins Arun Prakash sir, with a few words. Presently, he is working as an assistant professor in the Department of Chemistry, Sacred Heart College, Tirupattur, since 2012. Before that, he was working in Mahindra Engineering College, Namakkal. He did his master degree in Bishop Heber College, Trichy, Master of Philosophy in Bharatdasan University, and PhD in Periyar University, Salem, in the year 2011. He has received various awards and fellowships like University Research Fellowship Award by Periyar University, Senior Research Fellowship Award by CSIR New Delhi in 2008, Sir C.V. Raman Budding Innovators Award in 2009, Sadhane Arvalar Award in 2009 by Sadhane Arangam Trichy. He also received award for excellence in co-curricular activities in 2001 and Best Paper Award in national conferences. He has published more than 10 research publications in reputed journals to his credit with book chapter by Nova Science USA and presented nearly 25 research papers in international and national conferences and seminars. He also served as a resource person in various forums. His area of research includes mainly nanobiomaterials and completed the projects funded by FTC Anna University Coimbatore and Tamil Nadu State Council for Science and Technology, Chennai. With this short introduction, I welcome Dr. V. Collins Arun Prakash sir to deliver the presentation on the topic Emerging Frontiers in Biomedical Science and Research. Sir, now the forum is over to you.
Good afternoon, everybody. Respected head of the department of the institution and the organizers of this conference, one-day conference, my dear faculty members, research scholars, and my dear students. Once again, a warm welcome and good afternoon on my own behalf. I would like to thank Dr. K. Vanitha Bharati for the kind information, kind introduction that she made. I'm indeed very happy to be with you this afternoon to share some of the views on my favorite topic and my research area, namely biomaterials. And I'll be talking to you for the next few minutes about the importance and how it has emerged over the years as a very successful material. And this material could be a material for the future also. Therefore, I thought it would be nice and fitting to share this information with the young research scholars, faculty members, and also with the students, so that they can have a thought about it, and if they are interested, they can also contribute their own to the whole domain of biomaterial research. So, with this few words, I would like to straight away open my presentation, and we'll see what biomaterials means to us and to the whole research area. Give me a minute. I'm sorry. Uh, Let me do it again. Uh, can organizers tell me that whether I'm audible? I'm sorry. Yes, yes. Is my PowerPoint visible now? Is my
Yes, sir.
Yes,
is
sir.
my, okay? Uh, is it okay? I'm going to the second slide. You are able to see it?
Yes, sir.
Okay, right. So my topic, I request the organizers, suppose if there is any technical glitch, kindly let me know so that I'll be able to adjust it accordingly. Okay, right. So my topic would be on as it is printed. It is the emerging frontiers in biomedical science and research. Of course, this has become my very favorite field. Right from the day I started my research at Periyar University, I started concentrating on all these facts about biomedical science, its advances, everything. Okay, and at the outset I would like to thank Dr. J Indra for giving me this wonderful opportunity to share my thoughts on biomaterials. I've segregated my whole talk into two parts. So the first part, taking the consideration of all the audience present here, I'll be giving the preliminary aspects of what biomaterial means and how it is needed in day-to-day life, especially for patients or for people, those who really need it. Okay, so that details I will give, and also I'll try to give on a bird eye view of what is happening in the biomaterial research. There are a lot of materials that is emerging, and you know that this medical technology is improving day by day, and no one cannot stop with what we have. So therefore I'll give you a bird eye view on what is happening overall in the whole world. I would say how this biomaterial science and research is developing. And later on in my second part, I will be talking about my own research and what I have learned along with my research group in probing these biomaterials. Okay, so I will do that. Right. So with this point in mind, I'll straight away go to the definition part of it. And I think many of you might have heard this word, but some of you might not have heard this word, biomaterials. So it is, we can define it like this. No, so it's a simple material which can be kept inside the body. That's all. No, though the scientific definition goes differently, but still use we can use any simple definition, like if you can keep it inside the body, you can keep it inside the body, then that material can be simply called as a biomaterial. Okay, then of course we have got lot of types of biomaterials that we can look for, but those biomaterials has to fulfill this criteria. Okay, some important criteria or biocompatibility and bioinertness, bioactivity, etc. Very particularly, this biocompatibility is a very important aspect of a biomaterial. We cannot simply keep a material inside the body without knowing it that it is a biocompatible. What is biocompatible? It should not give any adverse reaction inside the body. Okay, so that's the main property that a biomaterial should have. And I want you to understand that in most of the cases, the body rejects the foreign materials. Anything that is kept inside the body kept inside the body at first will recognize it as a foreign body, and immediately there will be some kind of host response. Immediately the body will show some response. Now, just now we have just come out of this COVID situation, and you know how this virus can go inside the body and tackle the whole system, and sometimes it can make it worse, because when the body reacts to the virus, and it triggers a lot of reactions, and unless and otherwise it is properly treated and properly tackled, it ends up in a different situation. Therefore, similarly, even though the biomaterial is a biocompatible, I mean, biomaterial is good for the body, but still it has to have a biocompatibility aspect, so that it will not make any adverse reactions inside the body. Okay. And second, another important property that it should have is bioactivity. That means it should be also able to interact with the body. Not only that it should not produce any adverse effect, but also it should be able to interact with the body in a very positive way. I have given one or two examples here where it specifically involves the interaction with the bone. Okay, right? So we call it as osteointegration, where the material that is kept will react with bone. It can react with sometimes with the teeth. It can sometimes react with the tissues. Okay, so all these reactions are favorable, but it should not end up in any kind of toxic activity. So we desire for a biomaterial the property of bioactivity, and in terms of bone and dental related things, we desire something called osteointegration, osteogeneration, and things like that. Okay, so that is the main point, main property that a biomaterial should have. And we have seen what is a biomaterial. A material that can be kept inside the body for a therapeutic purpose. Now these are all the biomaterials that are available in a whole spectrum of let us say marketing or biomedical technology. These are all the materials available. So the main material are polymers can act as biomaterials. The many polymer materials can be safe and they can be used as a biomaterials. Ceramic materials can be used. Of course, they too have a very good property of bioinertness, bioactivity, etc. I will be talking by my favorite area is somewhere here, ceramics, synthesis of bioceramics. I'll talk to you when I touch about the research work. And then, of course, they are also being used as semiconductor materials that can be used for applications like biosensors. We talk about implantable microelectrodes. All these things are being slowly emerging, and at one point of time, our body can be sensed with all these novel devices. Okay, we are not far from that day where we will have all these devices. And of course, another very important group of biomaterials are metals and alloys, I would say. So these materials are also having this property of mainly bioinertness. And I think we have seen people in the subsequent slides. I will be showing how metals can be directly used in for orthopedic and dental applications in particular. They can be simply fixed inside the body, mainly because of their bioinertness. And the bioactivity of it, scientists are still studying, and they are trying to do it, how to make it bioactive. But the bioinertness, the what you call the mechanical rigidity that it can give, makes the metals to be very much used as a biomaterial, which can be implanted inside the body. Okay, right? I will talk to you on the next two slides about all how these biomaterials can be used. Now this slide gives you a broad idea of how different materials can be used as a biomaterial in different parts of the body. Okay, so I would say from the head to toe, almost everywhere, we can use the materials to be implanted inside the body. Okay, so it depends on the need, depends on the therapeutic need, we can go for it. So whatever I mentioned in the previous slide, that is there, except semiconductor materials. You find all the other materials, polymers, ceramics, metals, everything being presented here, okay, right now. So here we talk about, I briefly I'll tell one or two. See, here you have a lenses, which is made up of acrylates and silicone based materials. And wherever the bone comes in picture, we can always have metals, alloys. See here, you can see 316L, titanium alloy. All these metals can be used. Polymers can be used. See here, I have given a list of polymers: polylactide, polyglucosate, PMMA, polymethyl methacrylate. All these materials can be used as very successful biomaterials to treat some of the vital ailments or vital defects a person goes through. Okay, right. Now I'll skip this slide, because I'll come back to this again. I want to give you a brief development on how biomaterials have emerged over the years. Okay, right now, this is a very old area. In fact, it has been researched for let us say over a century, something like that. But still, they started with the first generation of biomaterials where they concentrated only on bioinertness. I was telling you about the metals and alloys. I know when you keep it inside the body, it stays there for a lifetime. And then time and then needed, suppose if it is, if you want to remove also, you can remove. Nothing big adverse reaction takes place inside the body. Therefore, they were, I mean, people were using the first generation of bio materials, which concentrates mainly on the bio inertness. But later on, there came a situation where they have to improve the implant materials and biomaterials. So they started looking at how bioactivity can be imparted to the biomaterial. Okay, so if you refer to the literature in the late 80s, 1980s, you can always find the word bioactive biomaterial. They used to add this word. So they want to emphasize on the fact that this biomaterial is bioactive. Okay, it is bioactive. And then now, of late, after this era is over, I would say the third generation of biomaterials, they really concentrate on a much higher goal of what we call it as a tissue regeneration or tissue mineralization. All these concepts have now come in, and now they have come to a point where they use biomaterials not only for bioinertness and bioactivity, but also for tissue regeneration. That's the much advanced aspect of a biomaterial. And this aims at even looking for a chance where the patient will gain back the tissue. Okay, whatever it is lost, he will be able to gain back to some extent, to some or greater extent, he will gain back. So now the recent research, for the past, let us say, 2 decades, it has been the research has been concentrating on the regenerational aspect of the thing. So these are all the generational evolution that has happened in the biomaterial science. And now these are all, I mean, old stuff in the sense, because they were using gold fillings, wooden materials, some materials, just to supplement what the patient needs. Suppose the patient has have lost a kind of part of a bone or a part of a teeth, or whatever it is, by accident or by old age, things like that. They used to substitute it by using some materials, and then they were successfully treated. But it was the very preliminary, what you call, stage or aspect of the treatment in biomedical technology. But later on, they started using some advanced materials, so that, as I told you, the second generation of materials that came into the picture. And here I have made few slides where these are all some common materials that are available for available in biomedical technology, where people are replaced with artificial valves inside the heart. And they can be treated for heart blocks and things like that. No, mainly made up of polymeric materials, which are very flexible, and you can use it with much ease. Of course, the cost part of it is there, but still you can use it. And this is another very important area where we are all familiar with. And these informations I just give to the people, so that whatever we encounter in the day-to-day life, those things can be converted as a research, or those things can be concentrated for improving our research. Though they are slightly preliminary in nature, as far as the research scholars or faculty is concerned, but I just want to leave this information with the what you call student, I mean the mainly with the student participants, and then they couldn't handle. You would have seen people who had lost their teeth and then going for an artificial teeth. Okay, right? So that's a very common issue. We many people now, many times they have dental caries, they have some kind of dental problems, okay, like increased sensitivity and things like that. They go to a dentist and then do some treatment. All these things involve the application of biomaterials inside, and this is the, maybe I would say, the extreme case of biomaterial application uh, in terms of dental implant. Okay, so when somebody has lost the teeth, and the whole set of teeth is being replaced by a dentist. Okay, now you see there are two parts in the dental implant, and this part, base part, where you see something like a screw, is a metallic part, is the base, and the top part we call it as a crown. Okay, the visible teeth part we call it as a crown. So it is actually made up of two parts, where the both of them comprises of biomaterial. Now I choose this example because I know this is a very classic case where you use a biomaterial for the entire application. Now this is actually, if you visit a dentist, and for a what you call as a tooth replacement, he will ask you to do it in two stages. No, it is not done at a one stage, it is done at a two stages. So what they will do is, first they will fix this, what you call it as a base part. So they normally this material is made up of titanium. In the first or second slide I was telling you that titanium is metal, is titanium, and titanium is metal which can be successfully used as a biomaterial, and therefore you will have a kind of screw. Of course this is made by manufacturers suiting to the needs of the gum and other things. So they will first make an incision here and fix the implant inside, maybe make a kind of screwing and then fix it. So only the screw will remain there, and they will put the sutures and things like that. It will be remain there, and it will remain there in the gum, let us say for 15 days, 20 days, or 1 month, something like that, depending on the healing perspective of the patient. And then once that is done, then the top portion is fixed, the crown part is fixed. Okay, now this is a ceramic and other composite material that is being made, and you can look at in this photograph that how it can perfectly match the original teeth. Okay, so this type of materials can really restore back the what you call the inconvenience and everything that a patient undergoes. So the whole setup is kept inside the body, and one is made up of a metal and another one is made up of a ceramic material, and both is assembled in a very nice way and then kept inside the patient. And once this is done, the patient gets back its normal comfort and easiness of using the using the lost teeth. Okay, so he gets back the normalcy. So that is how this biomedical technology and the biomaterial can be really helpful for a patient sometimes who undergo a lot of ease and discomfort. Okay, right? You know that the teeth and all these things, it makes a lot of aesthetic sense to human beings. Therefore, the all these things can be it can be restored back with the help of the biomedical technology, and dentists are very successfully doing it, and there are lots and lots of novel materials coming up in order to replace the lost dental materials. Okay, right. Another thing, of course, I already explained to you that how this dental implant is being fixed step by step, and finally you are restored back. And also now there are also, the lot of studies that are being done to make this metal biocompatible with the adjacent tissues. Okay, dental material, the tooth material should accept this metallic implant. So a lot of surface modification and other techniques are being made. So I think we'll get more and more novel materials in the future. This polymeric material, intraocular lenses, I've already touched upon, where we can go for using a polymeric material as a intraocular lens. Okay, when people suffer with this eye defect, they can be replaced with the polymeric material, and then they can restore back their vision. And another important type of biomaterials and implant materials that are available are vascular grafts. Okay, now these materials are also made up of polymeric composites, where it should be made as a flexible materials. So any kind of blood vessel damage or any kind of vascular complaints people have, it's a very serious complaint, where because you need a very flexible system to support that part. Okay, right? So they will, if the surgeons will surgically remove the um, affected part of the, the vessel, blood vessel or whatever it is, and then they will substitute it with a complete biomaterial, a flexible polymeric biomaterial, and then make the patient feel comfortable if they are suffering from some kind of heart complaint or blocked blood flow, things like that. People are able to do it. Okay, and at this juncture I would like to also talk about, I have not included it in this slide, but also people are already they have developed something called artificial tissue. Okay, right? So where there are some tissue defects, where people suffer with some burns or any other problems related to skin. Scientists have successfully developed what we call it as a artificial skin, a flexible polymeric material which could support, which could be used as a covering and heal the wound. Okay, and also there is another area where people use ceramic materials, biomaterials, as in the area of wound healing. Okay, so wounds can be healed, especially for people like soldiers, you know those who are in defense, when they have some problems, when they get some wounds, it takes a lot of time and medicines and things like that for them to get recuperated. Now they have come up with something called a ceramic materials, where it can used as a used in wound healing. So we'll discuss it. So I think one or two slides afterwards we have. And another important area, in fact, this is my area of interest, actually, to have materials for the orthopedic defects. Okay, for the orthopedic defects, I have shown a simple example of hip replacement, and people who had undergone this will very much know, how this process is done. And now this is called what we call it, what we call it as a hip socket. And you can see that there is a ceramic polymer composite, a white color composite, followed by a stainless steel ball. So we call it as a hip and socket. This is how our bone is there. So our natural bone is there. So when people have this hip degeneration due to some accident or by some other kind of musculoskeletal problems, so what they do is they go for this hip replacement. Okay, on the right hand side I have shown how these models are available. Now this is a hip replacement model that is available, of course, with the in the pharmaceutical market it is available. So when people have this kind of problem, they take the measurement and then design a kind of hip and hip prosthesis, we call it as. They design it according to their need, and then that is being implanted inside the body. Okay, now this is the hip bone, and inside the body, it is being implanted, and then of course it is left there. So what happens is, this arrangement, this hip and socket arrangement, this hip prosthesis gives the patient a lot of scope and a lot of comfort. Once it is fixed inside the body, the person is really able to walk or do his day-to-day activities in a very nice way. Okay, so that it's also very great lot of discomfort within the patient. And all these things are, it is made up of biomaterials and biocompatible materials. Many times when they do the surgery, it lasts for years and years. So it has to be very biocompatible and bioactive inside the body. And this ceramic material is made as a composite, so that it will provide a very soft interface. And here you have the silvery part is normally made up of 316L stainless steel, medical surgical grades stainless steel. And there are cases where they use sometimes titanium based alloys. And then this rod again is mainly based on, made up of titanium, in order to give enough rigidity. Okay, right? So that portion is being made up of titanium, and they are fused together. That whole thing forms the hip prosthesis. Okay, right? This is one of the very successful treatments we have in the field of orthopedics, where hip replacement is being done with a great success. And also there is something called total knee replacement, TNR, total knee replacement. Similarly, this many people have the complaint of arthritis and knee degeneration, all these things. When people, especially when they get aged, or when they have to face, I mean, when they go through accident and things like that, they have a problem with the knee replacement. The same thing can be done with the what you call total knee replacement also. That is also can be done, where the whole knee joint, the whole knee joint is being removed, and then it is kept with uh, I mean, it is substituted with metals and alloys. Okay, so the whole the movement of the knees can be restored, and people can take back their normal life. Okay, that is the major I mean, application of these two. And apart from this, there are also no other applications where, as I showed in the previous slide, from top to bottom, there are many areas where these biomaterials can be of immense use to the people. And it all depends on what kind of treatment they undertake for their ailments. And nowadays, because of the so many factors that are in country like India, we are in need of lots and lots of biomaterials to make the people feel at ease and comfort, so that they can resume back the normal time if at all they go through some problem with regard to bone and I mean dental and other things, I mean, concern. Now, as I told you, this now this research is slowly moving towards what we call it as the tissue regeneration aspect. Okay, now these are all some of the researches that are being done, where they come up with novel materials like osteopontin and other things, where they make use of the biomaterial interaction in order to make the material bind with the bone and other areas. Okay, right. So therefore, my specialization or area of interest is in orthopedics and dentistry. Therefore, I have chosen some materials where it is directly healing some bone related defects. So I have chosen this osteopontin as an example to be given before you, where this can bind with the fibronectin and other things. It can produce osteoblast, and therefore the whole bone regeneration is possible. Okay, so now there are every day we come across a material, a novel material, which can be very successfully used as a biomaterial. Okay, but therefore people are looking at composite biomaterials, where it can be used in combination with the one or the other. Say for example, I think in the some of the slides I told you that a polymer ceramics. Now people are using something like composite. They combine ceramic and a polymer and then form a composite. They try to form metal and a ceramic. Okay, so that composite is possible. Sometimes all three. These approaches are being made, because so that each one has got its own merits and demerits, and therefore in order to overcome that, they combine what we call it as a composites, and then prepare it. And but of course, the present idea is to not only provide a biomaterial or a implant as such, but also the idea is to provide the bone regeneration as such. Okay, the that technology, that need is felt strongly among the researchers, and therefore they do a lot of work in preparing such materials which can induce bone growth, tissue growth, and the tissue regeneration. Okay, so with this, I conclude the first part of my presentation, which gives you a general idea about what are biomaterials, what are the types of biomaterials, and what are its scope and its uses in a different field. Okay, so that is where, so I mean, I present this because if you are interested in pursuing some work or the other, it will be always useful. And in the second part of the work, I will also tell you about how very simple the work, and the simple in the sense very comfortable or tangible to carry out this work in our own situation. And then not only that, we can also publish very nice research papers and get due acknowledgement and I mean acknowledgement from the scientific community by pursuing a work. And also we have a satisfaction that we are producing some material, or we are involved in a research that is directly related with the human health and welfare, okay, in the area of biomedical science and technology. So that is what my aim in the second part of my lecture, that I mean the talk I am going to give. I would like to just know the organizers, is everything is well? Should I pause for a while for listening to the questions, or I'll finish the presentation and take up the questions? Thank you, madam. Thank you. Okay, so I will continue, so that I mean you will reserve your questions towards the end of the session. And now I would like to move on to the area of research that I am doing. Of course, my area of research directly overlaps with the ceramic biomaterials, to be in particular. Of course, I have also done some work in metal and alloy, based biomaterials. A little of work in that. So I'll be presenting about that. Now, my as I started my research, it was I was doing some survey, and then finally I landed in attempting a material called hydroxyapatite. Okay, that is the material that I have chosen for my research, and I am pursuing it until now because of its various applications we encounter. No? Primarily, as I was telling you, emphasizing in my previous slides, though the main application comes in the field of orthopedics. Okay, so it is very successfully used as a orthopedic implant material, either as a direct material or as a composite inside the human body, and it has been approved or recognized as one of the very best materials for bone based replacement. Okay, not only that, if you refer to the literatures, there are also other very good applications available, like it can act as a it can act as an absorbent. It can be used in the field of catalysis, in the field of drug delivery, of course, in the field of chromatography as a very good absorbent, and of course, people are also very successful in using it as in the field of tissue engineering, water treatment, all these things. They involve. But my presentation and my area of work would mainly deal with the implant applications. Okay, the implant applications. Okay, now this is the compound I have been researching. It is basically a calcium phosphate compound. Okay, so our bone is essentially made up of this material. Okay, it's basically a calcium phosphate, but the thorough analysis says that it is made up of hydroxyapatite based material. Okay, of course the collagen is there, bone collagen is there, other things are there. It's all present as an intermingled compound. And but this material, among all the materials, there are other calcium phosphate materials also, like tricalcium phosphate, octocalcium phosphate, etc. They are also quite good in giving good results when used as a orthopedic material. But hydroxyapatite is being widely researched because of many familiar properties that it has got, like bioactivity, biocompatibility, etc. It is very much non-toxic. It binds. It tends to bind with the bone in a a good way. Okay, right. Therefore, chemically it is similar to the human bone, and that all these things makes it a very competitive biomaterial to be used. Okay, so I know started working in this material. So my focus is like two or threefold. Number one, how to synthesize this hydroxyapatite biomaterial through various synthetic methods, and then of course check the biomaterial for its biocompatibility. That is the second step. And then further on, I have also attempted on how to make this hydroxyapatite, it's a bone like material, to be used as a coating material. Okay, so how to use it as a coating material. So that's what I have been doing. Okay, because the actual need is, when you have some implants, or when you have a material like this, see, basically this material is made up of a metal or alloy, followed by another type of metal or whatever it is. Now scientists have felt and doctors have felt that instead of this instead of this metal, they always prefer to use this metal along with the coating. So what we call it as call that as a coated implants. Instead of plain implants, bare implants, one can go for a coated implants. Now the task is twofold. What is that? No, one first thing is to prepare the biomaterial, maybe hydroxyapatite or whatever it is. So prepare the biomaterial, and the second one is to coat the biomaterial over the implant surface. Okay, so now if you happen to visit orthopedic doctor, you will definitely have these two choices. They will offer you either a bare implant or a coated implant, and of course, needless to say, the coated implant is always costlier, durable than the ordinary implant. So what happens is the challenge becomes even more higher, that when you go for a coated implant, this coating has to be durable inside the body. Okay, both it should have kind of what you call friction resistant, wear resistant for to be moved inside this socket, and also it should have all this biocompatibility, bioactivity aspects, so that it will not affect the other tissues. Okay, now hydroxyapatite is a very good material that can be used in the used as an implant material. And now is it okay? My slide is visible, background. Thank you, thank you, thank you. Okay, now what is this is the major need of selecting this material. Now looking at the population and the age classification of the population, you know that the number of people undergoing this bone related ailments is going higher and higher. Okay, and if you refer a orthopedic surgeon, he will say several thousands of surgeries are being performed, and one of the important problem is the cost of the surgery, right? The orthopedic surgeries, implant surgeries normally costs as in several lakhs. Therefore, a common man to afford a very very durable implant, it becomes slightly difficult. Many people do not undergo this surgery because of the cost reasons, because the surgical implants are very very costly, especially these coated implants. And if anyone near to you have undergone this surgery, you can just make an inquiry. You will see that most of the multinational companies offer these implants. Most of the implants are being imported. Of course, there are also companies which produce our own implants, but in most of the cases they are being imported, and then imported ones have a higher cost, higher claims about durability and other things. Therefore, people normally go for the best one, right? They opt for the best one, and then if you refer the statistics of the what you call the business that they make, most of the implants, the multinational companies makes the best out of it, and still now we are mostly importing the implants, and then they are to be used. Of course, there is a great need. That's why I tell in India we can make a very good progress in this biomedical research, if at all we are able to give a very good best product to our people, so that we can stand. Okay, right. Now these are all some statistics that I have called out. This orthopedic market is always picking up. Okay, right. So not only it is for health and hygiene reason, but also it is also deals a lot with the economy status of the country. Okay, so a country like ours can become a really leader in the orthopedic market, if at all we are able to develop a durable implant in par with other implants that we get right now, right? Okay, so these are all some challenges that we have, and these challenges makes us to move forward in preparing materials that are durable. Okay, right. So my aim, or when we make these materials, my aim is to go for a successful material that can be used as a coating, for orthopedic and dental. So whether this material that we make can be successfully used as a biomaterial. Okay, right. So that is the thing. And now when we use biomaterial, I mentioned two of it. One is the metal part, and another one is the ceramic part. So the combination becomes very perfect, because metals like titanium, alloys like 316L, stainless steel, all these things provide a very perfect what you call support to the bone. You know that our bone has got an enormous rigidity, and of course elastic modulus and other things. Mechanical strength is very very high. Therefore we need to use a material which can really support our bone. Otherwise, a patient may not feel the comfort. Therefore, now it combines the two, beautiful functions. One is the the rigidity that is provided by the metals like titanium or alloys like stainless steel, and also the bioactivity that is contributed by the ceramic. Okay, so now that is the combination we make. Okay, uh, see here we have this ceramic material, hydroxyapatite material, which can be bioactive and things like that, bioactive, which can contribute properties like bioactivity, biocompatible like that. But the problem here, as a ceramic biomaterial, is it lacks mechanical strength. It can be directly cannot be used in load bearing applications. That's the problem we have. But when you have the combination of these two things, both the metal and the ceramics, and then you combine two essential properties that are needed for the bone restoration. One is the mechanical strength aspect of it, rigidity aspect of it, and also biocompatibility aspect of it. Okay, so I told about total knee replacement. See there, that is the whole knee is being is being cut off. It's taken off if somebody has got a severe knee problem, and then that is being substituted by the biomaterial, suitable biomaterial. Of course, you can already I've told enough about this dental replacement. See, the dental replacement can be very perfectly done, and one can really get back, the aesthetic look or whatever it is, comfort with regard to, uh, you know, uh, any dental problems that they have. Okay, now how to make these hydroxyapatite metals? I will straightly go into my research, and there are some methods available in the literature like hydrothermal, sol gel, microemulsion, ultrasonic. All these things are available. A lot of other methods are also available for successfully synthesizing the biomaterials. And I'll be I very much focusing on hydroxyapatite and based hydroxyapatite based materials. So I will confine with the time available and the scope available. I will confine my discussion with regard to these methods. So these are all some methods. In fact, most of the methods we have attempted, and a few of them came out to be very successful. And we are working on a few more methods, so that whether we will be able to get yeah, what you call superior biomaterial, so to say. And I just share this information with the students, so that they, when they do their MSc project and things like that, they can very well take up a simple method like a hydrothermal method or sol gel method, even microemulsion. If they have an ultrasonic facility, microwave, a small microwave oven with them, they can very well take up this ultrasonic method, microwave method, etc. Of course, mechanothermal method, it needs some ball milling devices, things like that. So if the laboratory supports, I'm sorry, there is a small typo here. If they have some such materials, they can very well go for the synthesis of nanomaterials, especially hydroxyapatite in particular. Okay, right. No, simple the simple autoclaves. This structure, these instruments. If you have with a Teflon vessel, and you can simply do a hydrothermal method, within, let us say, within a day or two, you will be able to successfully synthesize a material. And if you can tune the experimental parameters, you can definitely end up with a nanomaterials. Okay, I do a lot of work in nano materials, especially with hydroxyapatite, with the primary purpose that when you have a nano material instead of a bulk material, it always have an edge on the tissue regeneration or the bone, what you call bone formation, because it goes, which matches well with the bone. And then there is a great possibility of what you call it as cell viability, okay, in bones. So the bones can grow, so that opportunity is always there. So one can easily attempt these methods. Simple laboratory equipped with a few instruments can help you to get these methods. And also, we have been concentrating on something called a coupled methods, where we make use of more than one method in order to achieve a biocompatible material, especially nanomaterials. So that that attempt have also paved results, fruitful results for us. We have clicked on two or three methods where we were able to get a successful nanomaterials. So as I was telling you, my efforts during the past years have been to do two things. Number one is to synthesize these material, hydroxyapatite materials, biomaterials, and then to make what you call implantable surfaces coated with this biomaterial. And that's the second part of the work that I do. So initially we started with this synthesis of biomaterials. Um, we were, I mean, initially starting with hydrothermal method, microemulsion, and then sol gel, all these routes. And this we have successfully published way back in 2008. Where I mean, this is my first publication. In fact, as a matter of fact, that we were able to report successfully the formation of hydroxyapatite through a ultrasonic coupled sol gel route. Okay, right. So we really wanted to see the effect on the sol gel method, conventional sol gel method, because normally these sol gel routes take a lot of time. Even hydrothermal method takes a lot of time for nucleation and other things. Therefore, we wanted to just enhance it the efficiency by ultrasonic coupled method. Of course, we have attempted microwave method also, in order to reduce the time factor, because roughly you tend to, I mean, you spend only 1/5 of the time for the experiment, in the sense they are so much fast, ultrasonic and microwave, and therefore you get, and we're able to successfully report the formation of this hydroxyapatite. This is the typical signature we get for a hydroxyapatite material. A simple FTR machine and XRD analysis would confirm the formation of hydroxyapatite. Okay, so it's a very stable material. In fact, if you attempt to do it in your laboratory, you will understand that it's a very what you call stable material, and it can be separated very easily from the reaction setup, and it can be characterized also. The quantitative production of hydroxyapatite is also very much possible, because the yield, everything can be enhanced. So that gives you a lot of opportunity to do further investigations. Okay, right. So this is our first attempt, and we continue to do a lot of we continue to attempt a lot of methods on that. Okay, this is our next work regarding the synthesis of hydroxyapatite. And of course, as you see in the first one, I had a great chance of collaborating with one of the organizers, Dr. J. Indra, of your college, and we were able to publish a paper on this, where we attempted a very different technique called soft solution freezing method. That is that paved a very good control over the reaction, and we were able to make a material out of it. And followed by that, we were also using some of the what you call the chelating agents like oxalic acid and things like that. So whether we're trying to see whether this calcium can bind with oxalic acid, like calcium EDTA complex we have, something like that. We were able to try to chelate the calcium using some material in the presence of ethylene glycol, and we were quite successful in doing that. We were able to produce hydroxyapatite powders. Okay, right. And later on, I was using also several types of additives, surfactants, growth regulating agents, and things like that. No, so this our public in this the paper, we have attempted some agents like dimethyl sulfoxide. Of course, later we have used PVA, polyvinyl alcohol, and other materials. In fact, CTAB, acetyl trimethyl ammonium bromide, this cationic surfactant, is also very good in yielding as shape controlled hydroxyapatite powders. Of course, I have not included that paper in the slide, but if you search that, you will find CTAB, cetyl trimethyl ammonium bromide, that can act as a very good surfactant, and lot of papers have been published. So we too have attempted and published one or two, one I think so. But later on, no, one of my students started with doing it with dimethyl sulfoxide, and recently, I think last 1 or 2 years before, we were able to publish it, where the shape control was really good. Okay, so we were able to get good shape controlled reactions, and hydroxyapatite material possible, because different applications require different types of what you call shape modulated biomaterials. Sometimes these shape modifications help the biomaterial to act in a very better way inside the body. Therefore, we have just done some experiments on that, and we have published it. And these are all the this is about the another method that we have attempted, apart from hydrothermal and other things. We have attempted microemulsion method using different types of surfactants. And again, the usage of surfactants have always has always um, yielded very good results in types of shape control. More or less spherical shaped particles we were able to get with the particle size reduction. Okay, so these surfactants have always helped us in regulating the particle size. Okay, that is one thing. And you can see the particles, these elongated particles have become slowly changing into spherical dimensions because of the template effect, that it because these surfactants act as a growth regulators, right? So that is possible. And if you refer to the literature, you can see lot of papers reporting this hydroxyapatite in different shapes. So nanofibers or fibers possible. We ourselves have done one paper in nanofibers, nanorods, and what else? Some people do it in nano flowers. They have reported nano flowers and nano whiskers, etc., etc. No, they produce different types of shapes so that they can suit the different need of a biomaterial. Okay, right. So again, this is another work that we have my student had done on the combination of DMS1 PVA as a growth regulating agent, again with the same microemulsion method. And here also the growth control was found to be very nice, and we were able to produce nano hydroxyapatite powders. Okay, so these are all some results that we have done with regard to the synthesis of nanohydroxyapatite. And following that, the second part of the work is on developing hydroxyapatite coatings on some surgical grade materials like 316L, titanium, etc. I've done few works in that. So what we do is, we try to coat this hydroxyapatite over the implantable material, and then do some evaluation for the coated material, whether it is durable inside the body fluid or other aggressive mediums. Okay, so that is the type of work that we do. So this here also we have done some work on making hydroxyapatite coatings over the biomaterial over 316L stainless steel, and we are tested for various the dissolution analysis, whether it is stable in the simulated body fluid and other things. So we have done. Our results are quite good, and of course there are a lot of progress to make in this direction. Of course, I have also published another work in how to coat the material. The coating method itself we have proposed, but of course I have not included it in here. So many methods can be used, like sputtering method can be used, electrode deposition methods can be used, uh, spin coating methods can be used. So every coating has its own pros and cons, but our aim is to produce, let us say, uniform coatings. Okay, that is the main point in attempting different methods, that we'll be able to give a very uniform coating over the implant because it can be durable inside the body fluid. Okay, so the work is on, and we are still progressing and trying to make. And of course one of our aim is to do the coating on direct implant material itself. Okay, so that is our aim, and one day or other we'll be able to make some coatings, presentable coatings over the real implant material itself. Okay, that is where we are progressing, and this is what I am doing and pursuing at present. uh, Maybe I'd like to close with a word of thanks to all the people who had helped me over the years for doing this research. So I'd like to thank the Periyar University for their funding, and also for giving the good opportunity of doing research. I'm very grateful to my research supervisor, Dr. D. Gopi, professor of chemistry in Periyar University, who had been my motivation and inspiration for doing the research. Of course, my sincere thanks are due to my friends, very close friends and collaborators in research until now, Dr. Govindaraju and Dr. Indra of VCW, for their wonderful effort and wonderful help throughout the years. At present, I am working in Sacred Heart College, Tirupattur, an autonomous institution. Where we are supported with a lot of help in doing this research. Of course, the last three, four papers that I've shown is the result fruits of what this institution is doing to us. So they have been offering even research grants to us. I received one. Through that, I pursued some research, and we did a lot of work out of that. So I would like to thank the management and all the people in Sacred Heart College for their wonderful support. Of course, I'll be really failing in my duty if I don't thank my own research scholars, very particularly Miss Ivenda. Right now, she is there and she had submitted a thesis. So much of the work she did, and helped me in carrying out the research. So I also thank other research scholars right now in my team for their wonderful help. Of course, for this rare opportunity, I should be always grateful to the Department of Chemistry. I profoundly thank the head of the department, all the professors, and especially the organizers of this seminar for giving me this very beautiful opportunity to interact with the research scholar staff and students. Of course, last but not the least, I would like to thank all of you for your patient listening for the past 45 minutes or 50 minutes or so. Thank you so much for your patient listening. Shall I stop at this point? And almost I have done. So thank you so much. And if there are any questions, I can take it up and then answer them. Uh, so with that, I would like to once again thank you and close this presentation. So now the forum is open to questions and over to the moderator. Thank you.
Sir, good afternoon, sir. Sir, I'm Dr. S. Malati. Sir, I have one query, sir.
Just a minute. Yes,
Ah,
madam. Can you hear me? Yes,
yes, sir,
yes,
yes,
madam.
sir. Audible,
Yes,
sir,
ma'am.
audible.
Yes, ma'am.
Sir,
Thank you.
a lot of biodegradable materials are there.
Yes, ma'am.
Among all, which one is the most resistance and how long does it take to degrade, sir?
You want to know the biodegradable material.
Yes, sir.
Uh, See, scientists always now they talk about, instead of biodegradable, they talk about something called bioresorbable.
Okay, sir.
Bioresorbable, because sometimes what happens, this degradation process often sometimes leads to some kind of it may lead to some kind of infections, and always remember, it is going to be let out in the body fluid, and subsequently either it has to be excreted, or it has to be retained as a harmless material. Okay, so that is the challenge they have. But in spite of that, they have developed some kind of biodegradable, the biodegradable materials are still used inside the body, especially when it comes to what we call it as a sutures, stitches and things like that. Mostly they are made up of a polymeric composition, so that they will slowly get degraded inside the body. Now people, they started thinking about more bioresorbable, like calcium based materials, where it can go into the body without doing any harm.
Okay.
Okay, right, that is the approach that they do.
Okay, sir. Sir, one more question, sir.
Yes,
Sir,
madam.
this is a general question. Sir, it is very difficult to publish a paper in elsewhere, sir, generally. How to send in the paper and publish, give your publications and give your information, sir. Information or suggestion.
Okay, at the outset, I would say, if you think it is difficult, yes, it is difficult. But at the same time, people are doing it. We should take it at that sense. People are doing it, many people are publishing it, and why not we? That is the kind of strength and courage a researcher should have, and even the faculty should motivate them to do, to publish a paper. I would say, no, in one sense, I would say it is not difficult. I would say it is not difficult. And we should really think what stops us from doing that. What stops us from doing that? Or, when a paper is rejected from a journal, now on what grounds it has been rejected? That we have to really analyze. Okay, right? But if you ask me, I mean, is it possible to publish a paper? I would say definitely say yes. In the sense, of course, there are some hurdles. You have to spend a lot of time and things like that. See, if you strategically ask me how to start, how to do that, you should right from the start, your ambition or your motto should be to publish a paper. So what does it
Yes,
mean? Right from the place when you start the problem, you should be, you should have a foresight that whether this work could be published.
okay.
Suppose you find that this work has got a less scope of publishing or things like that, then I would say better to stop that, because the scope of it is less. Therefore, right from the start, you have to see whether, suppose it is not possible, then you have to really put in a kind of a different type of effort. And I am personally of the opinion that you know ideas ideas make sense. I mean, ideas are costly, I would say. And sometimes I tell my research scholars also that the time you spend in the literature should be more than the time that you spend in the laboratory. That is what I
Yes,
say.
sir.
The time that you spend with the literature should be more than the time that you spend in the laboratory. Not that we haphazardly do something and then try to publish it. Once you got the result, XRD, SEM, TEM, whatever it is, all costly results you have with the hand, and trying to publish it. And the sometimes the reviewers say that it has already been published. Okay, already
Yes, sir.
such work exists in the literature, something like that. Then it's a kind of a heartbreaking situation for a
Mhm.
research scholar and a
Yes,
faculty.
sir. Yes,
So
sir.
look before you leap. First you try to, I mean, assess whether this work is publishable. I will tell a small experience that when I was doing with CTAB, I got fed up with the papers that came, because many such papers were there. But still now, to my surprise, still now people are publishing papers with CTAB as a surfactant. I think Dr. Indra would watch for this, because she herself have done a lot of work in that. So there is a scope. We have to find how. So to say, I would say we have to find the loopholes where we
Okay.
can really hit and do that. If you ask me, is it possible? I would always say yes, it is possible. It is
Okay.
possible. Of course, it is. It requires a little of our time and energy. Hope I
Okay.
have answered your question.
Yes, sir. Yes, sir. Thanks a lot, sir. And thanks for your valuable information, suggestions, sir. Thank you, sir.
Thank you. Thank you, ma'am.
Good evening, sir.
Yes, madam. Good evening.
Sir, I have one small doubt.
Yes, madam.
You have said so many things about the coated implants.
Yes, madam.
In the angioplast, drug delivery stents have been inserted to the patient.
Yes, yes,
So
yes.
whether they also come under this category of coated implants, sir?
No, no. They are grafts. We call them as grafts, because
Yes.
when you say implant, that should substitute a part, either it is a bone, teeth, or something like that. Rather, these grafts are actually inserted inside the defective valve what we have. So
Yes.
they are no flexible polymeric material which are given, I mean, inserted inside the existing valves, and then the flow of the blood or whatever it is, that is being
Yes.
facilitated. Okay, so that is there. But of course, what you say, what suppose if there is a complete removal of the blood vessel, maybe there we may go for, I mean, what we call it as a, I mean, total implant material. Again, that is not made up of metal, mainly made up of polymeric mesh like materials. There, they attach it and then do it. So both ways they do it.
Sir, is there any substitutes available for the nervous system, the coated implants, damaged nerves, whether it can be replaced by the artificial ones?
Now, people are working in the area of what we call it as a biosensors, where this nerve conduction and other things can be regulated. They do it with a kind of what we call it as a biochips and other things,
Mm.
so that they can pick up the sensory signals and things like that. a lot of research are being made. So there is a very good significant progress in the field of biosensors also. People are doing that. So that is the substitute we can make for nerve conduction, nerve sensing, etc. Sensory part of it. That is the development we
Thank you
have.
so much, sir. Thank you so much, sir. Sir, it's a very nice presentation. Thank you
Oh
so
no,
much.
thank you so much. Thank you so much for your compliment. Of course, one of my what you call aim is that, of course, I have given some informations for the research scholars, of course, faculty members. My experience is slightly limited only, I would say. But for those students who are trying to do some research projects and things like that, you can, not that you should take hydroxyapatite. I am not recommending. I mean, the sense I'm not forcing you, but there are very good research works that you can take with very simple equipments we have. Many times they say the facility is not enough and things like that. Not needed. Very simple experimental setups we can have, and then publish a very good paper, get a very good scope out of the research. That is one point I would like to leave with the students, that the one thing you have to do is to go through the literature. You should have a thorough survey of the literature, try to find out what are the materials available, and then do a very meaningful and useful research, right? And biomaterials is one of the very potential areas where you can choose. Yes, so sorry for the interruption. Maybe if there are any more questions, we can take up.
Sir, good afternoon, sir.
Yes, ma. Good afternoon. Good afternoon.
Sir, can you say the required characteristics for biomaterial for medical applications?
What are the required characteristics?
Yes,
Characteristics. Okay. See, one of the primary characteristics should be bioinertness. It should not make any toxic effects inside the body. Bioinertness. That is a very desirable quality. Of course, in contrast with bioinertness, you should also have something called bioactivity. That means it should not produce toxic effect, but also it should somehow support the physiological, functions inside the body. And then, of course, we should have something called biocompatibility. It should become one with the body. In due course of time, it should somehow it should become one with the body. So these are all some very important characteristics that a biomaterial should have: bioinertness and bioactivity, and then biocompatibility. Of course, there are also other characters like osteointegration and other things, but these three, I would say, very primarily required by a biomaterial, so that it can be used inside the body.
thank you, sir.
Yeah, thank you. Dr. Indra, can I stop? I think I can stop my presentation, isn't it? You can, if you have any other slides, you can put. I'll stop my presentation. And before I close, I would like to again thank all of you for your patient listening, and posting some important questions, which will be useful for my further research. I would like to thank the Department of Chemistry, Valala College for Women, for this wonderful opportunity, and also for the organizers. Thank you so much. Thank you.
Good afternoon, teachers, the respected dignitaries, and my dear students. I'm Anuvashni from the PG Chemistry of Valala College for Women. Today's session has been really helpful and thought-provoking, actually, because we stepping into the research part of our life, we need a lot of informations and essential things which we have we have in our field, that is the field of chemistry, all the three webinars by all the three resource persons were extraordinary, and really we had gathered lots of information through this webinar. And it is the one of the most interesting and informative webinars I've ever attended. All the three sessions were like really thought provoking and insightful. A special thanks to my professors, um, my dear teachers, for organizing and such a very special webinar, which has been really very helpful. And also a very special thanks to our research person. Thank you, sir. Thank you, ma'am.
Good afternoon, all. So I am S. Yashmita from 3rd BSc Chemistry, Department of Chemistry, Velala College for Women. So I'm very thankful and I'm pleased to tell my feedback in the grateful session. I first of all thank all those research scholars, those who are down to the earth for us and make their wonderful time. And thank you so much for the Department of Chemistry and the faculty members to take our future in their mind, and they organize this kind of wide range of international seminars. So thank you so much, it was really amazing. And it's really awakening the eyes of students towards the um, future research and those departments and variety of research fields. Thank you.
Good evening to all. The smallest thanks is always worth more than the effort it takes to give it. On behalf of the organizing committee, it's my privilege to propose the vote of thanks on this occasion. First of all, let me thank God Almighty for making this seminar a fruitful one. I would like to take this opportunity to thank our esteemed secretary and correspondent, Sri S.T. Chandrasekhar sir, for his continuous motivation and support. I extend my gratitude to our beloved Madam Principal, Dr. S.K. Jayanti, for her encouragement in all our activities. I must mention our deep sense of appreciation for the most valued invited resource persons, Dr. Suguna Perumal, International Research Professor, Environmental Biotechnology Section, School of Chemical Engineering, Eknam University, South Korea, Dr. Bharat Govindan, Research Scientist, Department of Chemistry, Khalifa University, Abu Dhabi, and Dr. V. Collins Arun Prakash, Assistant Professor, Department of Chemistry, Sacred Heart College, Autonomous, Tirupattur, Tamil Nadu, for their immediate concern for our virtual international seminar on integrated approach of chemistry and material science for sustainable future, and for their articulate lecture that motivates the participants to pursue research in the upcoming fields of chemistry. I would like to acknowledge my gratitude to our head of the department, Dr. N. Vijaya, and all the members of the organizing committee for their support in organizing this seminar. My thanks are due to the non-teaching staff for their support. My special thanks to Ms. Meghla, Assistant Data Center, for her timely technical assistance in the live streaming of our seminar. Last but not the least, I express my thankfulness to the attendees from our institution as well as other institutions for their enthusiastic participation and cooperation in making this seminar a successful one. Let us wind up our seminar with a quote by our former president, Dr. APJ Abdul Kalam. A door is much smaller compared to the house. A lock is much smaller compared to the doors. And key is the smallest of all, but a key can open entire house. Thus, a small, thoughtful solution can solve major problems. We believe that this one-day seminar will inspire the young minds to involve in scientific contributions that will benefit the society. Once again, thank you one and all. Thank you so much for the opportunity. Thank you so much, sir.
Sir, thank you, sir.
Thank you so much. Thank you so much. I think I can leave, isn't it? Okay. Thank you. All the best. Thank you so much for
Thank you,
inviting
sir.
me.
Thank
So
you.
much.
See you. Thank you.
Okay, thank you so much, sir.